Welcome to the universe of the mind. You'll be amazed at the things that you might find in a galaxy far, far away. The secrets of our world will be exposed today.
Have you ever looked up at the night sky and wondered what everything is truly made of? We know about atoms, and inside them, protons, neutrons, and electrons. We've even smashed those apart to find even smaller particles like quarks. But what if that's not the end of the story? What if, at the very heart of reality, everything we see and interact with is made of something else entirely, something incredibly tiny and vibrating? Welcome to the mind-bending world of string theory. To really get what string theory is about, let's take a quick trip back in time. For over a century, physics has been ruled by two incredible yet fundamentally incompatible theories. On one hand, we have Einstein's general relativity. This is the theory of the big stars, galaxies, the fabric of space-time. It describes gravity as a beautiful dance, where massive objects curve space-time around them, and other objects follow these curves. It works perfectly on cosmic scales. On the other hand, we have quantum mechanics. This is the theory of the small atoms, particles, and the weird probabilistic rules they follow. It governs the other three fundamental forces of nature: the strong force that holds atomic nuclei together, the weak force responsible for radioactive decay, and the electromagnetic force that gives us light and electricity. Quantum mechanics is spectacularly successful at describing the subatomic world. But here's the problem. When you try to use both theories at the same time, say to describe the center of a black hole or the very first moment of the Big Bang, the math completely breaks down. The equations spit out infinities, which is a physicist's way of saying, I have no idea what's going on. This clash between the macro and the micro, between gravity and the quantum world, is one of the biggest unsolved mysteries in modern physics. We need a theory of everything that can unite them. And that's where string theory makes its grand entrance. The central idea of string theory is surprisingly simple, yet its implications are profound. It suggests that if you could zoom in on any fundamental particle, like an electron, you wouldn't find a zero-dimensional point. Instead, you'd find a one-dimensional, minuscule, vibrating loop of energy, a string. Think of a violin string. By plucking it in different ways, you can produce different musical notes. String theory proposes something similar. Each of these tiny cosmic strings vibrates at a specific frequency. A string vibrating in one way appears to us as an electron, a different vibration, and it appears as a photon, the particle of light. Another vibration, and it's a quark. And crucially, one specific vibration pattern would give us the graviton, the hypothetical particle that carries the force of gravity. In this elegant picture, the entire universe, with all its rich diversity of particles and forces, is just a grand cosmic symphony. Everything is composed of these same fundamental strings, just vibrating in different modes. It's an incredibly beautiful and unifying idea. For the first time, gravity isn't the odd one out. It's brought into the quantum family, described by the same fundamental object as everything else. This is how string theory attempts to heal the rift between general relativity and quantum mechanics. But as with any revolutionary idea, there are some pretty big catches. And the first one is a real head-scratcher: extra dimensions. For the mathematics of string theory to work consistently, our universe can't just have the three spatial dimensions we experience: length, width, and height, plus one dimension of time. String theory requires at least 10 dimensions, in total 9 spatial dimensions, and 1 time dimension. Some versions of the theory even require 11. So, where are these extra 6 or 7 dimensions? Why can't we see them? String theorists propose that these extra dimensions are compactified. Imagine a tightrope walker. From far away, the rope looks like a one-dimensional line. The walker can only move forward or backward. But for an ant on that same rope, it's a very different story. The ant can move forward and backward, but it can also crawl around the circumference of the rope. That circumference is a tiny, curled-up extra dimension. String theory suggests that the extra spatial dimensions are curled up in a similar way, but on a scale so unimaginably small, far smaller than an atom, that we can detect them with our current technology. They are everywhere at every point in space, but just too compact for us to perceive or move through. The specific shape of these curled-up dimensions is incredibly important, as it would determine the precise way the strings can vibrate. And therefore, it would define the fundamental constants and laws of our universe. Another mind-blowing prediction of string theory is the existence of brains. The word is short for membranes. In this view, our entire three-dimensional universe might be a brain floating within a higher dimensional space, sometimes called the bulk. Think of our universe as the surface of a pond. We can move around freely on the surface, but we are confined to it. The strings that make up matter and light the open strings have their ends attached to our brain, so they can't leave. However, gravity, which is represented by closed loops of strings, isn't tied down. These closed loops can travel freely between different brains and through the higher dimensional bulk. This could explain why gravity seems so much weaker than the other fundamental forces. It's because its influence is literally diluted, leaking out into these extra dimensions. This idea opens up even wilder possibilities, like the existence of parallel universes, other brains floating nearby in this higher dimensional space. It even offers a potential explanation for the Big Bang. Perhaps it was caused by the collision of two such brains. Now it's time for a reality check. As elegant and compelling as string theory is, it faces major challenges. The biggest one is that, so far, it hasn't made a single prediction that can be tested with current experiments. The energy levels required to see these strings directly or to probe these extra dimensions are trillions of times greater than what our most powerful particle accelerator, the Large Hadron Collider, can achieve. Because of this lack of testable predictions, some critics argue that string theory isn't really science, but rather a form of mathematical philosophy. It's a collection of beautiful ideas that we have no way of proving right or wrong. Supporters, however, argue that this is a long-term game. They point out that many scientific theories were untestable when first proposed. They believe that indirect evidence might emerge, or that new theoretical breakthroughs will lead to predictions we can test. One area of hope is cosmology. The study of the early universe and cosmic background radiation might hold faint signatures left over from the era when string theory effects were dominant. Another possibility is supersymmetry, a key ingredient of most string theories. Supersymmetry predicts that every known particle has a heavier superpartner. If these supersymmetric particles are discovered at the LHC or future colliders, it would be a huge boost for string theory, though not a direct proof. So, is string theory the ultimate theory of everything? The honest answer is, we don't know. It's currently the most promising candidate we have for unifying physics, offering a framework that seems to have all the right ingredients. But it's also a work in progress, with many different versions and a lot of mathematical territory still to explore. Whether it turns out to be the final answer or a beautiful dead end, the quest itself has been incredibly fruitful. It has pushed the boundaries of mathematics and theoretical physics, forcing us to ask deeper questions about the nature of space, time, and reality itself. It reminds us that the universe is far stranger and more wonderful than we can possibly imagine. Perhaps one day we'll be able to pluck these cosmic strings and finally hear the true music of the cosmos. Thanks for joining me on this journey into the heart of reality. If you enjoyed this deep dive into physics, don't forget to like, subscribe, and hit that notification bell for more explorations of the universe's greatest mysteries. See you next time.
Welcome to the universe of the mind. You'll be amazed of the things that you might find. In a galaxy far, far away, the secrets of our world will be exposed today. All is never what it seems. Is a world created by our dreams? Are we living in a simulation? Is the moon alien space station? Quantum is quantum does. Nobody knew just what it was. To this day we still don't know, but we won't stop exploring, no. Welcome to the universe of the mind. To the universe of the mind. You'll be amazed of the things that you might find in a galaxy far, far away. The secrets of our world will be exposed today. All is never what it seems. Is a world created by our dreams? Are we living in a simulation? Is the moon an alien and space station? Quantum buzz, nobody knew just what it was. To this day we still don't know, but we won't stop exploring though. Welcome to the universe of the mind.
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 Mind. To the universe of the mind, you'll be amazed of the things that you might find.